Hello and welcome to our presentation for senior design. Our project name is PV String Monitoring Solution. We are Team 5. I am Tyler Atkins. We also have John Rule and Peter Ranley, and our advisor is Dr. Raby.
A bit about us. We are all electrical engineering students minoring in energy smart grid. John has co-op experience at Duke Energy, Tyler at DP&L, and I, Peter Ranley, have experience at Honda.
Our project tackles a serious issue in solar, which is the lack of adoption of PV string monitoring. This is due to the costly adoption of it from the expensive CTs and PTs that are involved in it. Why is PV monitoring important? It allows for quick detection for ground faults for technician safety. It also allows for more data to be collected to allow for quick identification for performance issues with inverters or the array itself, which leads to higher power yields.
So for anyone who didn't know about ground faults, they're energized conductors meeting ground. It's trying to complete the circuit. A lot of times this is caused by damaged conductors, equipment, wires, old equipment, but nicks in the insulation, faulty insulation will cause it big time. Currently in the U.S., an average of 1,000 people die as a result of electrical engineering injuries a year, and another 30,000 non-fatal electrical injuries a year. So the solution, our solutions encompassing removing the big expensive part, the CTs and PTs. Those are thousands of dollars, and it's the most expensive part. So we're going to create a microcontroller circuit and attach it to the PV string. It's going to be composed of voltage, current sensors, MOSFETs, resistors, the Arduino itself, and then we're all going to take this information back to a central computer and interface it for people to be able to look at it.
The basic approach to solving our problem is to monitor the current in series and monitor the voltage in parallel to the PV strings. The resistors are used to step down the voltage for our various components. We plan to use a P-channel MOSFET to open and close the circuit, leading to the voltage sensor. We'll program a time interval into the microcontroller's logic to switch between these PV strings using MOSFETs. The purpose of this is to reduce costs and the complexity of our design. The digital board representation displays how our test circuit will look for a single PV string. Pretend the 9-volt battery is a PV string. All the components on the breadboard are powered by a 5-volt DC signal from the Arduino Uno. The left module is the Hall current sensor. We'll measure the magnetic field and send a proportional DC voltage signal back to the Arduino for the current measurement. The module in the center measures the voltage with a small shunt resistor and reports the voltage back to the microcontroller with I2C code. The right module is an OLED display that will be used with our prototype to display the voltage and current live, and it also uses I2C code. Lastly, a 5-volt DC signal from the Arduino is sent to the gate of the MOSFET to switch the MOSFET on, and this will be used when multiple strings are connected. Here's the schematic of the digital board in the previous slide, showcasing all the connections for a single PV string.
So the budget, the money, the fun stuff. So our total cost is over $5,000, but that's due to the labor. Nicely for us, we are not paid for this. So really what we're looking at is the parts on the right. So parts, this is the microcontroller stuff, the Arduino Uno, per se. We're going to need one of those, $23. PCB board, $30. The MOSFETs, those are going to be about almost $5 each. So, and then really we're thinking with tax, it's going to be $260. And we threw a little 25% contingency to say, hey, we destroyed a few resistors and our MOSFET's not working correctly. So that's about 25%. So we're thinking a little over $321. Gantt chart. This is our schedule. So right now we're in the research phase. We need to be worrying kind of about, Arduino communication and our software. And after that, we're going to be working on our initial design. That'll be starting about early November. Over November, we're going to simulate, and that'll take us on to prototype construction, the Arduino coding, circuit, the GUI. That's going to take up most of the last of our year from mid-November to the end of the year. And then design improvements and testing is the biggest part. Those kind of overlap. So as we're testing and finding things that we need to fix or improve, that's what we're going to be doing all of January and February. And then looks like we're going to be doing Duke testing, the big test, field test in early March. So then by the time, mid-March rolls around, we can work on our test results, documenting them, and creating our report.
Testing. Currently, the plan is to start testing the prototype at the beginning of January. During our first round of testing, we will be confirming the Arduino programming is correct. We will also be testing the insulation resistance of our project to confirm that it will be capable of handling the high voltage DC involved in PV arrays. And then we'll be moving to testing in March for final proof of concept at Duke. The concept map. In our concept map, the microcontroller is the main brains of our project. It will be communicating with our Arduino software for code to tell the Arduino what to do. The Arduino will also be sending data to the central computer, which will send data to our web interface, and which will interact with our GUI. Our Arduino will also be controlling the voltage sensor PCB, as well as reading data from the current sensor and control voltage sensor PCB.
We have several concerns for our project as we progress further. A major concern is whether our components will be able to handle a high DC voltage. For example, the current Hall sensor does not have a voltage rating in the datasheet, and our funding can be tight if we burn through our components. Another concern is if we need more research on creating an enclosure for our final design, as we do not have any experience with 3D printing. Our last concern at the moment is the accuracy of our measurements. What will be the difference between our theoretical and actual values?
Thank you for viewing our presentation. If you have any questions, please reach out to John Rule, Peter Ranley, or Tyler Atkins with any questions. Thank you.